Okay, so this is chapter 15 lecture. This is going to be your acid-base equilibria. And this is really just an extension off the previous chapter. So you're going to notice this is very closely tied to that previous chapter, chapter 14 in this case. And really, it's just applications of those same principles. Really, you're not going, if you understood the previous chapter, this chapter is going to be quite easy. Okay, so the common ion effect. Now, this is really just telling you the same sort of information that you've already actually gathered from previous counts. It's just now we've tied it together into a nice singular topic, which is common ion effect. So, as you may remember from your Le Chatelier's principle, a shift in equilibrium position that occurs due to the addition of an ion already involved in the equilibrium reaction. So common ion effect is really just what's named. If you add more of a common ion, one of the ions that's already in the equilibrium, it's going to shift it, of course, away from that ion. Or another way of saying it's just like Le Chatelier's principle, right? It's just now we're going to use that in a mathematical sense. We're going to use that in an ice table sort of sense. So let's look here. We have NH4 plus Cl minus here when they dissociate in water. And so if we add 1 molarity of this, if we add some of this salt to an NH3 solution, what would happen? Well, remember this salt right here, NH4 plus Cl minus, this dissociates when we add it to water, which would be our aqueous solution, right? And so that means what we're adding is really, we're adding NH4 plus, which is the same thing we would have seen down here. So remember that NH3 is a base. It's going to take on an H plus to give you NH4 plus in solution. And so, in solution, if you add this salt to this already established equilibrium, it will push it towards this direction because they have a common ion effect. Now, this may seem like you're probably going, oh my goodness, this seems like something new. It's not at all, okay? Really, we're just talking about the same thing we've already done a couple times in problems, which is we start with a concentration. We have an initial concentration of something. Okay, so we're, again, just going to be using Le Chatelier's principle now through that same mechanism we learned before, which is our ice tables, or our ice problems, if you will. So in solutions that contain polyprotic acids, your production of protons by your first dissociation is going to significantly inhibit the succeeding dissociation. This is one of the reasons why that second dissociation rarely makes any real difference, is because your initial H plus concentration already has a fairly large amount from that first dissociation of the acid. All right, so let's try this out. So here we have the equilibrium concentration of H plus in a 1 molarity HF solution is 2.7 times 10 to the negative second molarity. The percent dissociation of HF is 2.7%. Let's calculate the H plus and the percent dissociation of HF in a solution then containing 1 molarity of HF and 1 molarity of NaF. Okay, so first thing you want to do is you want to look here. This is a salt. That means it's going to completely dissociate in solution. That's why we use these salts. That's why we're talking about these salts. And so when you see this salt, you hopefully will see that this should give you a sodium plus and Na plus, which doesn't really do anything in this problem. That's just spectator. And an F minus. Well, F minus is going to be the same thing that's going to come off of this. That's the conjugate base, isn't it? And so what you have here is you have an ice problem again, where you're figuring out the H plus concentration. And then from that, from that ice problem, you're going to figure out the percent dissociation of HF. Now, what you have going in is you have an initial concentration of the HF and you have an initial concentration of the F minus. Now, interestingly enough, I'm going to point out before we get into the math that I said to you before, the more information you start with, the less information you have to find. And so what this means is adding more stuff in is actually a good thing. Don't think that that's bad, okay? Adding more information at the beginning means you have less math that you probably have to do. Okay, so let's go and do this. We do this the same way as before, all those other ice problems that we did last chapter. All right, so our major species and a solution containing 1 molarity of HF and 1 molarity of NaF. These are going to be the HF, of course. Then we're going to have a fairly large amount of F minus because of this right here. And we're going to have a lot of sodium, but that's not really important. And of course, we'll have a tremendous amount of water because this is a solution, aqueous solution. That means in water, right? It means water is always the most you have. All right, so right here, this is the acid. This is the HF going to H plus and F minus. That's simply the dissociation of an acid, right? And its equilibrium expression is, of course, the acid dissociation constant equals product of reactants. And remember, again, these acid ones are always very easy and straightforward because, by definition, it always is giving off 1H plus. So that means all these end up being to the power 1, and it's quite straightforward. All right, right there is your Ka. Remember, the position never matters for Kas. That Ka is true for this equilibrium at this temperature, whatever that happens to be. Probably room temperature. Now, the important concentrations are going to be shown in this following table here. And so right here we have the HF concentration that we start with. At equilibrium, we're going to use some amount of this HF up to produce H plus and F minus. And so this is the amount we use up, minus X, like we've done before. Now, in this case, we actually started with F minus, didn't we? And so we've started with 1 molarity of F minus. And that means at equilibrium, we're going to have 1 molarity plus whatever we have used up of the HF to make F minus and H plus. Now, the H plus, we're going to go ahead and neglect the contribution from H2O because, frankly, 10 to the negative 7 is just such a small number compared to these numbers we're seeing here that it just doesn't matter. So whatever H plus we make here, that's going to be so large that any contribution from water will matter. And so we will just put X. Whatever we made is the amount of H plus. All right, so we have our terms at equilibrium now. We can go ahead and substitute those in to our equilibrium expression here. And so we substitute those in right there. That's the X right there. That's the 1 plus X right here. And that's the 1 minus X down here. Now, you will notice again, we have looked and seen that, well, this is fairly small, isn't it? And so that X value right here, that's probably pretty small. That means 1 minus that value is going to round just back up to 1, isn't it? 1 plus that value is probably going to round right back up to 1, isn't it? And so we can ignore those plus X here and the minus X here. And just go ahead and solve the problem like so. We can assume that problem would equate to this. That this would be a very close approximation. That means you only have 1x here, don't you? And 1 divided by 1 is, well, 1. So you actually find out in this case the Ka is equal to x. So that x actually ends up being just our Ka value right here. All right, now this value is very, very small compared to 1. It is much less than 5%, so we're good. This is a good, acceptable approximation here. All right, so our H plus concentration will equal that X, as we set up before. And so that means the H plus concentration would be 7.2 times 10 to the negative 4 molarity. Now, if we take the negative log of this value, that's going to give us our pH. And so the pH equals 3.14 right there. Now, the percent dissociation, again, we're going to go ahead and use our percent dissociation will always be the concentration of the stuff that X that we go into ahead and made or lost, right? So that X right there is always going to be this top portion in these percent dissociation of these acids. And so we plug that value for X up here. This down here is always our initial concentration, what we started with, of the HF. And then we have to multiply by 100 to make it a percentage. And so we plug those values in, we do the math, and we get 0.072%. All right, so let's compare these values for the H plus and the percent dissociation of HF with those that we figured out from when we added our salt. And so when we just looked at the HF, we found that that value was 2.7 times 10 to the negative second molarity. Our percent dissociation then was 2.7%. All right, so that was a lot larger of a value than the one we found when we added the salt, wasn't it? When we added the salt, our H plus concentration went down considerably, which is 7.2 times 10 to the negative 4. That's a 100 factor almost. And our concentration of the percent dissociation of HF also went down drastically. So before it was 2.7%, now it's 0.072%. It's considerably lower, right? And this again is because we have a common ion in effect. That is the F minus ion. So that F minus ion is pushing the equilibrium towards the reactants, which is HF. That is causing the products to become less and less. And so yes, that's proving our common ion effect that we just learned previous to that. By the way, you may wonder why I do like these case studies and do problems to prove things I just told you. That's good science. Ideally, you should be trying to disprove the stuff I teach you. And interestingly enough, this year I actually showed a great example of this. A graduate student actually disproved and reinvented how you determine whether something's a metal or not. So things that were considered metallic, things that were considered not metallic, there's been a slight shift in that in the last year. And that is a great example of somebody looking at something they've been taught, being taught how it's being done, and going, that doesn't seem quite right, does it? And going ahead and coming up with a new way of testing, which it was quite brilliant. It was a very neat thing. So, which of the following statements is true? The HF dissociates more readily in a solution of NaF than in pure water. HF dissociates equally well in a solution of KCl and in pure water. Or HF does not dissociate in water to any extent. Well, we know HF dissociates somewhat because it's a weak acid. We know HF here, this has to dissociate less readily, right? Because again, dissociation would leave F minus. That would be a common ion with this, which is F minus, which means this can't push it toward the HF, having less dissociation. This right here, you'll notice that KCl does not have a common ion effect with HF. And so the KCl and pure water would be expected to be fairly close to each other. That should be a very close number. Now, because again, they do not have a common ion effect. All right, so buffered solutions. So a buffer solution is going to resist the changes in pH when either hydroxide ions or protons are added. So if you add a base to a buffered solution, it's going to resist change in pH. If you add an acid to a buffered solution, it's going to resist change in its pH. And that's what a buffered solution is great for, and that's what, by definition, it is. It resists change to its pH from adding acid or base. Now, the example of this would be blood. So blood will, this absorbs acids and bases, that are produced in biological reactions, and overall your pH does not change significantly. Now, when I say that it resists change to pH, yes, the pH will change very, very little, okay? However, it does change a small amount. Some people get it stuck in their heads that the pH will not change in a buffered solution. Yes, it will change. It's just instead of changing whole units of pH, you would change fractions of units. Okay? So this contains a weak acid and salt. That's the typical buffer solution. The buffering is possible at any pH. This is going to be based on your choice of your components. So you have to use an appropriate set of weak acid and salt, or weak base and its salt, to make a buffer solution at that appropriate pH. So let's try this first and see a buffer solution and talk about how this works a little bit. So a buffered solution containing 0.5 molarity of acetic acid, which is right there. Again, notice I use acetic acid a tremendous amount just because it is very easy to use and it's something that you've all encountered. 0.5 molarity of sodium acetate, which again is going to be the salt of the acetic acid, right? Or another way of saying is you're adding the conjugate base right here of this acid. And this Ka for this acid is right there. So let's calculate the pH of this solution. Again, you can do this as an ice problem. So again, you look at your major species. You have your acetic acid, which is your weak acid. You have the sodium, which is neither an acid or base, so we can just ignore that. And we have our conjugate base, which is that acetate anion. Of course, we have water, and water will act as a weak acid or weak base. This is always going to be in any aqueous solution a major species. And in fact, is actually what you're reacting as an acid or as a base, right? You always go through water when you're in a water solution. Now, the acetic acid dissociation equilibrium will control the pH of this solution. So when you're talking about buffers, what I want you to think about is a buffer is really just an equilibrium with some of each species on each side. So you may have noticed if you take a plank of wood, or if you take a seesaw and you press and there's no weight on either side, you can actually like move it with your finger, right? And it's very easy to move. So any weight introduced to a seesaw with no weight on either side is going to cause the entire thing to flip around whichever direction you want, right? And so that's like a normal acid-base problem. So a normal acid-base problem, you put some of this in, and you don't have any of these, right? And so it just goes whoosh and makes product, and it's just like a seesaw, right? Because you put weight on one end, there's no weight on the other end, so it just catapults up, skyrockets. Now, what happens when you have a bit of weight on both sides? So let's say we started with some of this, we start with some of this. Well, that's going to put weight on that seesaw in both directions, right? So if you try to move it with your finger, you're probably not going to do that anymore. You can't just add a little bit of acid and expect the pH to shift drastically anymore, because there's weight on both sides. Another way of thinking about this is if you add acid to this, there's already some of this, and so any acid added will just react some of this away. Okay, now let's go ahead and do this problem. So again, we started with some of this and some of this in our initial concentrations. And so we have actually made a buffer system. So right here, these are the initial concentrations we started with. Again, we're going to assume that our H plus is 0 because it's close enough. And so again, what do we end up with? Equilibrium. Well, we end up with the initial minus whatever we use for this. We end up with the initial plus whatever we have created or used of this one. And we end up with here with whatever we make, because that 10 to the negative 7th that was already there is so small it doesn't matter. Alright, so here's our equilibrium expression for our acetic acid, and it's just like every other time you've done this. Please make sure you have this down. This is the third chapter that you're doing these, and it should be fairly easy for you at this point. So H plus, the acetate anion, which is your conjugate base, and your acid. And that was the value you're given in the problem. So I'm going to go ahead and get it into an ICE table because that's always helpful to envision these. So again, these are the equilibrium concentrations that we get from the initial plus that change. And so we plug these equilibrium concentrations into our problem, our equilibrium expression, and we can go ahead and make the same assumption we've been making before. This value is very small here. 0.5 is much larger than that value. So we would assume that adding or subtracting x from 0.5 will make no difference. And so we go ahead and get rid of those x's, that plus x, that minus x. Remember, we always have to keep the ones that we're multiplying by. And that's 0.5 over 0.5 times x. Well, that's going to cancel, isn't it? And so our Ka actually ends up equaling x. By the way, I oftentimes set these up in the lectures so I don't have to have a calculator. And that's why they're always the same thing on top and bottom. So I don't have to do any math in my head. All right. So this is the x. Again, what does that x mean? Well, first off, let's make sure our assumption is correct. Is this value right here less than 5% of these values here? Yes, it is. It's much less than 5%. So our assumption was good. That x value is going to be your concentration of H plus. So our concentration of H plus is 1.8 times 10 to the negative 5 molarity. If we take the negative log of that, that'll give us our pH for 4.74. All right, so let's try another interactive example problem. So we calculate the change in pH that occurs when a 0.01 mole of solid NaOH is added to a 1 liter of buffered solution that we had in our previous example. So let's compare this pH change with what occurs when we add 0.1 mole of that solid NaOH just to water. And so, first off, we had a previous example, which is a buffer solution, remember. And that's the acetic acid with the acetate anion that we just looked at in the previous problem. So our reaction that's going to occur is this right here. We've added hydroxide ion into the solution, and that is making water, and it's salt. It's actually a salt if you're curious, but anyways, so we are deprotonating our acid, right? Just as we've done before. Now, this reaction, we're going to assume this reaction goes to completion, okay? And that is a very good assumption. It's almost always true, and for this problem, it definitely is true. And the great thing about that is you can just directly subtract off this concentration of OH minus that you make from that NaOH right off of your initial concentration of your acid, which is very nice. So let's go ahead and do the stoichiometry of this. So we have this reaction right here, which is again the acid being neutralized by that base, that NaOH. So we had here 1 liter of 0.5 molarity acetic acid. That means that would have had 0.5 moles. This right here was 0.01 moles. So what's going to happen is you're going to subtract the 0.5 by 0.01 is going to be used up. And that's because these are a 1-to-1 relationship, right? And so after this reaction, you're going to be left with 0.49 moles of the acetic acid. Now remember that when you're using up this acetic acid, you're making acetate anion, aren't you? And so you start with 0.5 moles of the acetate anion, and that 0.01 that's used up here is going to go to this. So we have to add that 0.01 to this right here. And so now when we have our initial concentrations of these, this one's going to be 0.49, while this one will be 0.51. Let's see how we've shifted those initial concentrations now. Keep in mind the OH minus, because this goes to completion, that's your limiting reactant that will be used up. All right, so we have done our conversion. We're again going to do the same equilibrium problem that we did before. It's just our initial concentrations have now shifted. And so, again, our major species, acetate, acetic acid, sodium, and acetate anion, and of course water. So our dominant equilibrium is going to be, again, the acetic acid going to the acetate anion. Our big difference in this case is going to be the same problem, but with new initial concentrations. And so our initial concentrations are those ones we found due to the neutralization of the OH minus. So again, our initial concentration for this is 0.49. Our initial concentration for the acetate anion is 0.51. Again, whatever we use up here, minus x, is going to be made over here, which are plus x's. And so this is 0.49 minus x, and 0.51 plus x. All right, so again, you're going to plug those right into your equilibrium expression again, which is actually the exact same as the previous problem. We just now have the 0.51 here and 0.49 here. All right, so again, this value of x, we would assume that this would be much lower, much smaller than the 0.51 here, or 0.49. And so we can get rid of the plus x, the minus x, to leave us with this relationship right here. Now, this means you're going to have to take this, divide by that, and then you will divide that over, right? And so we are given that x is going to be about 1.7 times 10 to the negative 5, and that's going to be pretty close to true. This value right here, again, if we take our 5% rule, well, this value right here is much less than 5% of either of those values. So, yes, that was a good assumption. Very good. Now, that value of x, that's going to be our concentration of H+, because that was what we set it as up here. See that? And so our concentration of H+ equals 1.7 times 10 to the negative 5. If we take the negative log of that, that's going to give us 4.76 for the pH. And so our change in pH in our buffer system is only a plus 0.02 change, which is a very small number for pH. Of course, that's a fairly large concentration change, and it would be a relatively significant one. But as compared to pure water, as we'll see in just a little bit, that's a very small change. And so our buffer system resisted pH change, which is a buffer, right? All right, so let's compare that value with what we would obtain by just putting in 0.01 moles of our solid NaOH into a 1 liter of water. If we were to put that in 1 liter of water, you would expect this to give you a 0.01 molarity NaOH solution. And again, we're assuming this 0.01 mole, first off, that's not a lot, is dissolving and not adding any volume to this, which it likely will not. It's fine. All right. So in this problem, our OH minus concentration is going to be all of the concentration of NaOH, because that will completely dissociate in solution, because that's a strong base. And so what we see here is our concentration of OH minus will be 0.01. So what we need to do then is we should go ahead and take this, the Kw, divided by the concentration of OH minus, and that will give us the concentration of H+. So when we do that, so here's our value of Kw, 10 to the negative 14. 0.01, you can also write that as 10 to the negative 2. And so this is just that concentration of OH minus. We do the math, and we find out the number is 10 to the negative 12. Now, if we want to get the pH, we're going to take the negative log of that value. And so the negative log of that is going to be pH 12. Notice the pH shoots up a lot if you just put pure NaOH into a non-buffered system. So the solution is now pH 12. When it was pure water, it was pH 7. And so now we have actually gained 5 pH units due to adding this 0.01 molarity of NaOH. So a huge shift in pH, right? You can see the difference between adding a base to a buffer system versus adding it to pure water is massive in terms of pH change. All right, so buffered solutions, these are going to be solutions of weak acids or bases containing a common ion. And remember, what you're doing is you're populating both sides of an equilibrium. So they always have to be the two species on both sides of the equilibrium to build up a buffer system. When a strong acid or base is added to a buffered solution, it's usually best to deal with the stoichiometry of that reaction, of that strong base or strong acid neutralizing it first, and then just plug those in as your initial concentrations. All right, so this right here is a graphical example of what I just told you. And so here we have the original buffered solution pH. When we add an H plus or OH minus, that's going to give us our modified pH. So how do you work these problems? Well, you're typically going to do the stoichiometry calculation first. So just literally add H plus, and that will convert the base to acid, right? Or add OH minus, and that will convert some of the acid to base, just like you were seeing in the second part of that previous problem. Then step 2 of all these problems is always doing the equilibrium calculations, that same ice table calculation all the time. And just remember, if you're doing a buffered solution, you're always going to have the initial concentration for both the acid and its base, or the acid and its conjugate base, or the base and its conjugate acid. So let's look at this example here. We have a weak acid, and how we represent all weak acids is by saying HA. It has a conjugate base, which is A minus. So when we add hydroxide ions to this reaction is going to occur, which means you will neutralize some of the HA, the weak acid, to form some of the conjugate base, A minus. So the net result of these, of adding a strong base to a weak acid buffer system, is always the same result, which is OH minus ions are replaced by the A minus ions. And so you can always just directly convert that OH minus ions you added to additional A minus and subtract that off from the HA every time. So the stability of the pH under these conditions, we can understand that by writing this following expression. And you may notice that this is slowly leading you mathematically through to a overall expression for buffer systems. So we have here our equilibrium expression, right? And we can rearrange these so that we can get this relationship between the weak acid and its conjugate base over on one side. And so we have the H plus equals the Ka times the HA over the A minus. Notice we've just divided, multiplied, that's it. Okay, so we have now defined this H plus concentration based on a constant and a ratio of the HA versus the A minus. So whenever we add an OH minus concentration to these, whenever we add a base to a buffer system, the change in that HA versus A minus ratio will be fairly small because you're changing this ratio here rather than just a singular number. So when the small amount of OH minus is added to much larger amounts of the HA and A minus, your concentrations of HA and A minus will change by small amounts, and that means your pH will stay nearly constant. Okay, and so here again, this is just a graphic saying the same thing I just told you in case you're more visual. So when protons are added to a buffer solution of a weak acid with its conjugate base, so we're looking at the other way, where we're adding protons instead of OH minus. So again, your A minus in this case, which is your conjugate base, is going to take up those protons, being converted to the weak acid. And so yes, you get the same sort of relationship, it's just in reverse now. We're adding H plus to the base, giving us the acid. And so again, your A minus and HA are both going to be large in comparison with this H plus. So your pH would then be a very small change. Now notice I have given you, if you go ahead and think on your own a little bit and do a little critical thinking, you will have noticed at this point that we keep mentioning this H plus or OH minus concentration is small in comparison to these concentrations. So a buffer system only really works if these concentrations are large in comparison to any acid or base you add. If you add large concentrations of acid or base to a small concentration of buffer system, it will destroy it, okay? You will no longer have an equilibrium. You will no longer have a buffer system. So these right here is the Henderson-Hasselbalch equation. I'm going to lead you into it. So we've already established that this H plus concentration equals the Ka of the acid over its conjugate base. Now remember, if we're looking at pH, that's the negative log, isn't it? And so if we take the negative log of both sides, we're going to get this relationship right here. Negative log of H plus equals negative log of Ka minus the log of that relationship right there, which is the HA over A minus. Note you want to keep that relationship together because that's actually what we're manipulating in all of these equilibrium problems. And so negative log of H plus, well, that's pH. Negative log of Ka, that's pKa, isn't it? And this doesn't really have a nice fancy moniker, so that's negative log of HA over A minus. So your acid over your base concentration. All right, we can inverse this so that we get a positive here. By the way, if you look up the Henderson-Hasselbalch equation, you will get examples of both of these. You might find this, the negative log, or you might find the positive log. Choose one to remember. It really doesn't matter which one you do. Technically, this is actually the Henderson-Hasselbalch equation right here, which is the pH equals the pKa plus the log of the base over the acid. And again, that's remember that the equations we always usually want to keep everything adding, right? We typically try to avoid minuses if we can. All right, so for a particular buffering system, all the solutions with the same ratio of A minus to HA will have the exact same pH. So for example, right here we have a 3 molarity of the acetic acid, or 5 molarity of the acetic acid, excuse me, and 3 molarity of the acetate anion. And so we would get a pH for this that would be based on this 0.6 ratio. If we had a 100 times smaller concentrations for both of them, that will still give us our ratio. And so it doesn't really matter, the ratio of the concentrations is what matters here, not the individual concentrations. So if we divide both sides by 100, you still get the same ratio, you still get the same pH, you still get the same pH from the Henderson-Hasselbalch equation. So if we were to plug those values in for those values for the table, we would see both of those solutions would give us a pH that is 4.52 for that buffer solution. They would give us the exact same pH. If we were to measure both of the pH probe, we would get the same value. One is a vastly more powerful buffer than the other, though. This is a very weak buffer. This is going to easily be overwhelmed and destroyed. This one has a lot more concentration. This would be a much stronger buffering, which is called buffering capacity. All right, now, in our Henderson-Hasselbalch equation here, one of the things I would like to point out is this same sort of equation setup is a very common setup in many other equations for entirely different purposes. So you will oftentimes see a tabulated value with an experimental condition modifier, which is what this is. And so that's actually very common. You're going to see the same sort of setup, and they'll all sort of look a little bit alike. So be aware of that. know that you can sort of memorize them as a group and have them in your head as a group, where it's always tabulated value plus the log of some sort of experimental conditions. Typically, it's product over reactant, in this case, base over acid. Okay, so our assumptions that we've made here. We've actually made an assumption when we were doing this problem, and that's that the equilibrium concentrations of the A minus and the HA would be equivalent to the initial concentrations, which is a very common assumption we've been making, right? And so yes, we are assuming that these initial concentrations can be used here, and you can go ahead and do that for most problems. All right, so let's go ahead and give this a try. The buffered solution contains 0.25 molarity of NH3, which is a weak base, and 0.4 molarity of NH4 plus. And of course, I've just went ahead and said NH4 plus instead of the NH4Cl, haven't I? So calculate the pH of the solution. So our major species we're concerned with are these right here. So there are the NH3, the NH4 plus, and the Cl minus, which are both from the NH4Cl that will dissociate in solution. And of course, every aqueous solution has water, because that's the major species, period. That's the one that is the one with the most amount. Now, the Cl minus, this is a negligible basicity. We can ignore that. It's just going to float around and do nothing. The H2O, on the other hand, is a weak acid or base. If you really want to know whether this Cl minus does nothing, I get asked this problem every now and then, usually by people that are more interested in being a natural chemist. And yes, it actually does. It does have a small amount of effect. It's negligible for our purposes, but if you ever go into analytical chemistry, yes, this will have an effect. This will actually create what's called an ionic effect. Okay? Anyways, you can learn more about it in a later class. So the NH3, this is the reaction for our base reacting with the water, which will be our acid here, and forming that NH4 plus OH minus. Again, this is the equilibrium expression. How do I know that this is the reaction I need? Well, again, that's my base, that's my acid. There we go. Okay, and so we have our equilibrium expression right there. Notice this is the equilibrium expression for a base. So it'll be Kb over here, which is what we were given. So our ice table for this is going to be our initial concentration minus here whatever we use. And that will give us our equilibrium concentration of 0.25 minus x. So again, this will be initial concentration plus whatever we make for these. How do I know I'm making these? Well, I don't start with any OH minus here, do I? And so I have to make this side the product. I cannot make the reactant because I don't have any OH minus to make it. All right, so 0.4 plus x. This doesn't start with any significant amount, so we'll just go x for the equilibrium concentration there. We plug those into our equilibrium expression, and so that will be 0.4 plus x times x there. That will be 0.25 minus x on the bottom. Again, we would expect, due to this Kb being fairly small, that these x's will also be small. And so, plus a small number won't make any difference, minus a small number won't make any difference. We can ignore this plus x, this minus x, leaving us with this right here. Notice it's a lot easier to take 0.4, divide by 0.25, and then divide that over than it would have been to do the other problem. And so we get x equals 1.1 times 10 to the negative fifth. Now again, that is a small number compared to 0.25, and so that fulfills our 5% rule. So our concentration of OH minus will be that 1.1 times 10 to the negative fifth. If we take the negative log of that, that'll give us the POH, which is 4.95. Now, the easiest way to get the pH is usually just get the POH, subtract that off of 14, and that will give you your pH of 9.05. So this case is a typical of a buffer solution. This is a good example of a weak base and its conjugate acid making a buffer solution. The initial and equilibrium concentrations of the buffering materials are essentially the same. They're close enough that there isn't any significant difference. The solution will contain large quantities of the NH4 plus and the NH3. And so your following equilibrium expression can be used to calculate the OH and then the H plus from our KW, which is this right here. So the H plus can also be directly can be determined using the dissociation equilibrium of the NH4 plus. So right here we see the NH4 plus. This would be the dissociation concentration of the dissociation equilibrium of the NH4 plus. By the way, I kind of dived into this, and some of you may not have caught that this is an alternative solution. We've already figured out the solution to this problem. I'm just working it from a different direction and showing you what could have been done. Okay, so our Ka value for NH4 plus, this can be obtained from our Kb value. How do we do that? Well, we always take the Kw divided by the Kb in this case will give us the Ka. And so we take Kw divided by that Kb we were given, and that'll be our Ka. So if we were to use the Henderson-Hasselbalch equation then, well, we can just go ahead and plug in our K, which we have now, plus the log of our initial concentration for the base, 0.25, that we were given in the problem, divided by 0.4, which we were given in the problem again. That will give us, if we solve this and then take the log of that, this will give us negative 0.2. And so it'll be 9.25 minus 0.2, or 9.05. And you'll notice we get the same answer. And this is actually slightly easier if you think about it. This, you don't even have to do most of this previous work where we wrote out these equilibriums. What you can just recognize is that you have an acid here and its conjugate base. And so you just need to get the Ka for this from this one's Kb. That's it. Once you have a Ka, you can use your Henderson-Hasselbalch equation for buffers, which is right here. And of course it makes it really easy, right? You can just plug it in. Ta-da. There you go. You don't have to tabulate values, you don't have to do stoichiometry, you don't have to do any of that. Alright, so which of the following will not produce a buffered solution? Alright, so what we're looking here is we're looking for a weak acid and a buildup of its conjugate base, right? Or a base and its buildup of its conjugate acid. And so the one that does not produce this is going to be a base with base added to it. Now let's look at some of these other ones, because some of you may be going, how does that work? Okay, so in these cases you have a base here, and this is adding an acid to it. So this acid will actually neutralize part of this base here, about half of that. See that? That's 100 milliliters versus 50. And so what that means is you'll be left, after you add this HCl, you'll be left with this base and its conjugate acid, about half and half of each. This right here is again a base. Again, we are adding HCl to it, and we're neutralizing again about half of it. And again, that's going to give us a base and its conjugate acid, which is a buffer, right? You're doing the same thing over again. You're just neutralizing a lot more of it this time. So you still have a base and its conjugate acid. Again, here you have a base and its conjugate acid again. You're just using different numbers in each case. This is the only one that you have a base and a base. You just have all base. You don't have any conjugate acid there. You are given a solution of the weak base, Novocaine, and its pH right here is 11. You add to this solution a small amount of salt, containing the conjugate acid, which is this Novocaine right here, which is the H plus indicates it's the acid, right? So which of the following statements will be true? Both the pH and the pOH increase. Both the pH and the pOH decrease. Both the pH and the pOH remain unchanged. pH increases and pOH decreases, pH decreases and pOH increases. Okay, so here at the beginning of the problem, right, I had Novocaine, which here is obviously a base, its pH is 11. And I've then added a salt that contains its conjugate acid. So I've added an acid to this, haven't I? So when you add an acid to a base, what happens? Well, the H plus increases and the OH minus decreases, right? And so in these cases that both of these would change in the same direction, that doesn't make any sense, does it? In this case where you think that you don't have any change, that also doesn't make any sense, does it? So your pH will get to a smaller number, your pOH will get to a larger number. Again, the pH and the pOH, because we know that they're related through the pKw, these can never move in the same directions. They always have to move in different directions. Okay. This might have been for different concentrations of a buffer, but this is definitely not that problem. So again, remember our H plus concentration increased, meaning our pH decreases. Our pOH will increase, meaning that the concentration of it decreased. So considered a buffered solution at pH 4 made of HF, which has that Ka, and NaF, which of the following statements will be true? All of the concentrations below are going to refer to your equilibrium concentrations. So, at pH 4, would you expect this HF to equal the F minus, or would the HF equal H plus, or any of these other things? So, the answer is going to be the HF has to be less than the F minus. How can I figure that out? Well, I can actually use my Henderson-Hasselbalch equation, can't I? So remember, my Henderson-Hasselbalch said the pH, which is 4 here, has to equal the pKw, or pKa, excuse me, which would have been the negative log of this value, times, or plus the log of these two, the F minus over the HF, right? The base over the acid. And so, I have here a 4. If I take the negative log of that, that is. So the negative log of this is 3.14, meaning that my 3.14 is smaller than my 4, right? So I need the concentration of my base to be larger than my concentration of my acid, so that the log will be of a number above 1, right, in my Henderson-Hasselbalch equation. And so I need the base to be a larger concentration than my acid, which is what that says right there. By the way, this HF equals H plus, most of these don't really make a lot of sense in the context of this question in the first place. So you actually could have eliminated quite a bit of those just by thinking a little bit about this, that this is a buffered solution. Anyways, again, it's E, which is the HF, is a lower concentration, the F minus. Again, that's because if you look at that Henderson-Hasselbalch equation, you can see that you would need a, remember it's the pKa, which is 3.1 something, would equal 4 over here. And so you will have to have a plus value. You'll have to have a positive value. The log of a value above 1 is positive. A log of a value below 1 is negative. And so I need my concentration of base to be higher than my acid. Buffering capacity. I already mentioned this before, but this is the amount of protons or hydroxide ions that a buffer can absorb without a significant change in pH. So the larger your capacity here, the more concentration of buffering components in the buffer. Another way of thinking about this is the larger those concentrations, that HA versus A minus, the larger the concentrations of HA and A minus, the more buffering capacity you have. Another great way of looking at it is the seesaw example I gave you before. The larger the masses on both sides of the seesaw, the harder it's going to be to change, right? So if you have two elephants on both sides of the seesaw, then putting a human on one end isn't really going to change that much, is it? What if you have two ants on both sides of the seesaw? Well, then putting a human on it is going to change a lot, right? In fact, you might smash the ant. Anyways, the concentrations, therefore, the larger the concentrations you have on both sides here, the larger the resistance to change. Okay, so this larger buffering capacity, what's important about this is that every time that you add H plus protons, or every time you add hydroxide ions to a buffer, these are going to use up some of that acid or base in that buffering system, right? And so the larger concentration you have, the larger buffering capacity you have, the more H plus or H minus you can add before you overwhelm your buffering system. So, I should cover that. Okay, let's look at this. Again, another problem. So let's calculate the change in pH that occurs when a 0.01 mole of gaseous HCl is added to 1 liter of a solution containing 5 molarity of acetic acid and 5 molarity of sodium acetate. For acetic acid, there's its Ka. Again, this is just going to be neutralizing one of the components first. Again, that same sort of thing we talked about before. We just use stoichiometry. We're going to have HCl, which is going to react away some of this acetate anion, isn't it? Giving us acetic acid. So you can determine your initial pH by just taking your initial concentrations and plugging them into your Henderson-Hasselbalch equation. So our concentrations originally are going to be equal. And so the initial pH is just going to be log of 1 here. The log of 1, well, that's 0. And so that's plus 0 there. And that means our pH in this case is just the initial constant pKa, or the initial negative log of the Ka. So our pH in this case is 4.74, which is what our pKa would be for acetic acid. So after addition of HCl, each of these solutions, the major species before the reaction will be like so. Okay, so this is the HCl right here. It's going to break completely apart into H plus and Cl minus. How do I know that? That's a strong acid again, right? And so that is going to completely dissociate. If you're wondering where the strong acids come from, you should have actually memorized 7 of the strong acids and way back in General Chemistry 1. And that's actually where that comes from. Now, this right here is your acetic acid. Sodium won't matter, of course. And right there is your acetate anion, which is its conjugate base. And of course, we always have water because this takes place in water. So, your initial reaction here is going to be your acetate anion reacting with the H+. And this is going to give you additional acetic acid. And so what we do is we just do a straight up stoichiometry problem here. So our 0.01 moles of added H+ is going to convert 0.01 moles of the acetate anion into 0.01 moles of the acetic acid. And so this is just a tabulated form showing you the stoichiometry. After we have done this reaction, we'll have no H+. We'll have lowered this number 5 to 4.99, which is minus that 0.01, right? And this number right here, which is our acetic acid, will have went up to 5.99. 0.01. Notice we move 0.01 from here to here. All right. So we can go ahead and put these initial values in now after we've added that H plus. And so we go ahead and just take our Henderson-Hasselbalch equation. We plug in our pKa we found before. We plug in our 4.99 from the stoichiometry, divided by 5.01, again from that stoichiometry. And that is going to give us 4.74 minus 0.0017. Notice these changes should typically be fairly small in a buffer system. And so that gives us, well, once we subtract that off, we're just going to end up rounding that right back up to the initial number. And so that ends up giving us just the same number again, which is 4.74. Doesn't make a large enough change to even matter. So due to the fact that we've added so little HCl, there's virtually no change in pH because we have such a high buffering capacity. So the optimal buffering is going to occur when the H plus HA is equal to the A minus, when we have the largest concentrations for both of these being equal. So the best buffer is going to have equal weights on both sides. Okay, that's the best analogy I can give you. It's going to have your same concentration of A minus as HA. That gives the most buffering capacity in both directions. So it gives us the most resistance being changed by an acid and a base that I can have. So the pK of a weak acid needs to be as close as we can get it to the pH of the desired buffer solution. So what we want is, if we want a pH of 4.7 for a buffering solution, then yeah, acetic acid would be great. If we wanted a pH of 3, it would not be that great. Or if we wanted a pH of 11, it would be completely unacceptable, right? So you want this pKa to be as close as possible to the desired pH of your buffering system. So a chemist needs a solution buffered at pH 4.3. You can choose from the following acids and their sodium salts. So we have here chloroacetic acid, we have propanoic acid, benzoic acid, and hypochlorous acid. I know I said the names, but ironically you don't even need to look at the names at all. What you need to look at here is the Kas. That's going to tell you which one you need here. And so we want a Ka that's as close as possible, a pKa, that is as close as possible to this pH, don't we? This one's relatively far. This one's pretty close, isn't it? This one's also relatively close. And this one right here is really far away. And so you would need to take the negative log of these values and see which one is closest to pH 4.3. And so we go ahead, we want these ratios to be as close as possible. We want HA to be equal to A minus if possible. That would give us a pH of 4.3. And so our pKa needs to be as close as possible to the pH. Now a pH of 4.3, if we want to get the H plus concentration, we want to undo the P, get rid of it. We take 10 to the negative 4.3. And that will give us a 5 times 10 to the negative fifth. And so we can compare those directly to our Ka values now. So we don't have to convert each Ka to a pKa. And so we compare that then to our Ka values here. And we see that this right here gives us a value very, very close to 1, doesn't it? This right here is very close to our 5 times 10 to the negative fifth. And that will give us a value. We want these values right here to be as close as possible to 1. This is the acid versus the conjugate base here, isn't it? So our benzoic acid, which was the one that's closest to 1 here, would probably be our best choice. That would give us our optimal buffering. And again, that's because these numbers are the closest. You can test that by figuring out these ratios right here and seeing which one is the closest to 1. This is how you actually show and prove this, by the way. We've done the work here to literally prove this to you, right? The optimal buffer is going to have a ratio here close to 1, and you can see here that this value is very close to 1. And so this is a very close ratio to what we want. All right, so a solution will have the most effective buffering capacity when the concentrations of the buffering components are what? Well, that's right here. My bold was on the wrong one. Okay, so the solution will have the most effective buffering capacity when the concentration of buffering components is as large as they can get, right? You want as much of the buffering components as possible. You want them to be equal but large in concentration. That will give you your most powerful buffers, the most buffering capacity, and the optimal concentration. So titrations. Okay, so we've done everything so far except we haven't really looked at experimentally how do we determine things like the concentration of an acid, or how do we experimentally determine things like buffering capacities. And so what we're looking at here is now we're looking at titrations. So this is going to be your experimental portion of these chapters. Now this is used to determine the amount of acid or base in a solution. A titrant is delivered from a burette into a solution that's being analyzed. So your titrant is typically what is the standardized solution. You know what the concentration of your titrant is typically. The stoichiometric or equivalence point is determined by the changing color of an indicator. Stoichiometric or equivalence point, the equivalence point is going to be where your number of moles of your titrant equals the number of moles of what you have in there. The titration pH curve is going to be a plot of the pH of the solution that you're analyzing as a function of the amount of your titrant that you have added. Now, many people get a little confused here in the fact that they get stuck on what I'm going to teach you right here. Notice that titration, I have introduced this as an overall technique with a lot of vagueness in these statements, right? I have not even indicated that this is acid, base, nothing in most of these statements. And so titration can actually be used for a lot of purposes. Okay, it's a very useful technique that has a wide range of applications. So please don't get stuck in your head that can only be used for determining the amounts of acid or base in the solution like this definition has. That's a very limited definition. It can be used for a very wide range of applications. So in an acid-base reaction, this is your net ionic reaction for these acid-base neutralizations. And so you determine the H plus at the given point in the titration will involve determining the amount of H plus remaining at the given point, dividing the remaining amount of H plus by the total volume of the solution. And this right here again is your net ionic reaction. Notice this is H plus plus OH minus yields water. And so when you add an acid H plus to a base OH minus, you make water and a salt typically. All right, one of the things you have to be introduced to here in these titrations, because typically you will not want to use full moles because that'll just be a lot of titrant. You'll end up doing a lot of work, is millimoles or mmol. So this is 1,000th of a mole, just like a milliliter, millimeter, all of these things, those are always a 1,000th of, right? And so 1 millimole is 1,000th of a mole. Now, the reason that this is very useful is you can define molarity, which is normally defined as moles per liters, right? You know, liters are fairly big, right? You don't want to have to dump 10, 20 liters into something, that would take a long time, a lot of effort. So instead, we can define molarity by defining it as millimoles per milliliters. And if you put millimoles on top and milliliters on bottom, then you're going to have 1,000 in both denominator and numerator. And that means that these are the same thing. They are both molarity, which is moles per liter or millimoles per milliliter. Now, the number of millimoles of solute is going to be obtained from the product of the volume in milliliters and the molarity. So again, you're going to take the molarity. If you multiply it by milliliters, you're going to get a number of millimoles. So let's go ahead and do a little case study. So let's consider the titration of 50 milliliters of 0.2 molarity HNO3 with 0.1 molarity NaOH. So when you have added no NaOH yet, the major species in this are going to be the H plus from here, the NO3 minus from here, and the water. And the pH is purely going to just be the H plus that came off from that nitric acid, because again, you have an acid in solution, right? And so what you start off with here is 0.2 molarity of HNO3 is going to have 0.2 molarity of the H plus ions, because it's a strong acid. And so your H plus concentration would be 0.2, and your pH would be 0.699. So when you've added 10 milliliters of the 0.1 molarity NaOH, well, that NaOH is going to react with that H plus, right? The OH minus that is going to be given off, because it's a strong base, is going to react with the H plus to give you water. And so your major species you're looking at are, again, your H plus, your NO3 minus, your sodium, and your OH minus. These right here have negligible acidity or basicity. They actually form sodium nitrate salt, which will say dissolved in solution. And of course, your water is what everything goes through, right? It's making water, it is going through water for all these reactions. So, our 1 millimole of this OH minus is going to react with 1 millimole of our H plus that was in solution. So before the reaction started, we had 10 millimoles of that H plus in solution. We're going to react it with 1 millimole of the OH minus. What that means is you'll have 9 millimoles remaining of the H plus in solution, and your OH minus will be reacted away. It'll be gone, because that's the limiting reactant. So once you've completed that reaction after adding a strong base to a strong acid, your major species that will be remaining are the H plus that you had left. There'll be the NO3 minus, the sodium, and the H2O. Again, you can use that H plus concentration to determine the concentration, the pH again. And vice versa, by the way. If you stuck a pH meter in there, you could, of course, determine the H plus concentration from that. Okay, so we have 9 millimole of H plus remaining, but we have changed the volume. Remember, we started with 50 milliliters of solution. We have now added 10 milliliters of that NaOH solution. So that means our total volume now is actually 60 milliliters. So our concentration has went down just from dilution as well. And so we now have 9 millimole divided by 60 milliliters, which is 0.15 molarity H plus. Now, to get the pH, we take the negative log of that, and that will give us 0.82 for our pH. So what happens when we add 20 milliliters now? Well, again, we just do the same reaction. So we had started off with 10 milliliters at the beginning. We've now added 20 milliliters of this, so that will be 2 millimole. And that's going to leave us with 8 millimole of the H plus. Again, we do the same problem for the concentration. So we have 8 millimoles that's remaining of the H plus. Our new volume is going to be the initial 50 milliliters plus the 20 milliliters that we added, right? So that will be 70 milliliters in the denominator now. And that will give us a concentration of 0.11 molarity. And that, if we take the negative log, is going to give us a pH of 0.942. So finally, we've added 50 milliliters of the 0.1 molarity NaOH. And if we do that same problem again, we're going to find the pH is now 1.3. Notice that these go up fairly slowly at first because, again, each pH unit is a factor of 10 change in concentration, right? So when we finally add 100 milliliters of the 0.1 molarity NaOH, the amount of NaOH we've added will now be equal to the amount of nitric acid we had. And so these will actually fully neutralize. This will give us the stoichiometric or equivalence point of our equation. And so the only major species at our equivalence point will be the salt and the water. This is the full neutralization of that acid. Okay? And so the sodium and nitrate, they don't have any significant acid or basic properties. They're actually a salt. The pH of this will actually be neutral because this is a strong acid with a strong base. And so your pH for this equivalence point will actually be neutral, 7. So what happens when you add 150 milliliters of that NaOH now? Well, this is actually going to completely overwhelm your H plus and leave you with OH minus, won't it? And so what we see here is we start off with 10 millimole of the H plus, and we now have 15 millimole of the OH minus we're starting off with. And so we've used up all of the H plus because that's now the limiting reactant. And we're left with 5 millimoles of the OH minus. And so this is now going to be a basic solution. The OH minus will be in excess. This is going to be what determines the pH. So I would do this problem by figuring out my concentration of OH first, OH minus. It's much easier. Now, you take that 5 millimole that's remaining of the OH minus, you divide it by the concentration, the volume at this new dilution, right, because you've added 150 milliliters into it. So that's 50 plus 150, giving you a total of 200 milliliters for your solution now. And so that will be 5 divided by 200, 0.025 molarity for the OH minus. Okay, so we know that the concentration of H plus times OH minus has to be 10 to the negative 14. And so we can take 10 to the negative 14, divide it by our concentration of OH minus, and that will give us our concentration of H plus right here. We take the negative log of that, and that would give us our pH. And so we see here that that pH is 12.4. All right, so if we were to do 200 milliliters of NaOH, again, this is going to completely overwhelm the H plus again, and you would again just find the concentration of the OH minus, just like we did here in this previous one, and use that to find the H plus using the kW. Now, that pH would then be 12.6. And what we get if we plot these out, so right here is that titration curve, or the pH curve for the titration, which is the pH right here. We started with an acid. We've then added the titrant right here, which is our NaOH. And this right here, this X, is going to be our volume of NaOH we added. And what we see here is we start with a very small value for our pH because this is an acid. As we add base, that value goes up slowly. Then we're going to start overwhelming it and completely using up the H plus. Once we've hit the equivalence point, we'll have used up all of the H plus, all of the OH minus will use up all the H plus, and they will both end up being 0. They will be equal for the equivalence point. Or stoichiometrically equal, right? For the stoichiometric point, if you will. All right, now, on this part right here, the second half, we're going to start adding excess NaOH. And so this starts creating a buffer. The more excess NaOH we add, the stronger the buffer will become, the stronger the base, not buffer, base will become, and the higher the pH will get until it gets to a plateau here. And this will plateau up here, and it will never actually reach 14. This will actually be based on the strength of this base right here, because the strong base, this goes up very high. All right, so we actually have sort of three sections, if you will. We have where there is excess H+, we have where they're equal, which is the equivalence point, and then we have after the equivalence point, where we have excess OH- in this study. So let's consider the opposite, where we have a strong base and we are adding a strong acid as the titrant. So you are, in this case, going to start with excess OH-. As you add H+ to it, it'll use up that OH-, giving you lower and lower pHs. Eventually, you will use up the OH- completely, and you will have the equivalence point, where the H-, OH- and the H+ will use each other up and be equal in number of moles. And that will give you, in this case, a pH 7, because these are a strong base and a strong acid. Their conjugate base, conjugate acid are going to be things that have negligible acidity or basicity. So you always end up with salt water, essentially. All right, so the next part after the equivalence point is going to be where you add excess titrant. And so this acid is the excess titrant. The pH will go down rapidly at first. You're soon going to get close to where it would be just for the solution of HCl. And that's what you're seeing right there then. So again, you determine that H+ just by excess HCl that's in there for a strong acid being added to a strong base. Now, let's look at the titrations of a weak acid using a strong base. So in the case of a weak acid, you can determine the H+ after a certain amount of strong base has been added. This will involve considering your dissociation equilibrium of your weak acid. Because remember, the weak acids will not fully dissociate. So yes, you will neutralize some of them, but they'll all be like those neutralization problems we looked at before. Whenever I show you the graph, there's another way of looking at it, and I'll talk about that. So, though the acid is weak, it will react to completion with the base. However, the H+ concentration will be based on the dissociation of the weak acid. The pH at the equivalence point of a titration of a weak acid with a strong base will always be greater than 7. It will never be 7, it will be greater than 7. The reason for that is a weak acid has a weak base as its conjugate base. What that means is when you've completely reacted away all of the acid and left the conjugate base, you now have a base in there. You don't have a neutral solution, you have a base. And so the pH will always be above 7 for the equivalence point of a weak acid. Alright, so the stoichiometry problem for these, you will have the reaction of the hydroxide ion with the weak acid. You always assume that to run to completion. So you always take that amount of OH- you added, and you always subtract that off from your millimoles, usually, of your weak acid. The concentrations of the acid that remains and the conjugate base formed thus will be determined just from this stoichiometric problem, which are quite straightforward and something you've practiced a lot. The equilibrium problem. So the position of your weak acid equilibrium will then have to be determined, and the pH will be calculated from that. So one of the ways you might want to think about this weak acid being neutralized by a strong base, titrations, is you have a weak acid, right? What happens when you convert some of that to its conjugate base? Well, you have a buffer, don't you? And so the first part of these problems is actually really a buffer problem. And you're going to see they're just like the buffer problems we looked at before. You subtract off the amount of OH minus you added, just like we did before, right? And then you figure out the equilibrium concentrations, just like we did before. And that's going to be straightforward, just like we did before, same buffer problem. You can even use the Henderson-Hasselbalch equation. So let's go ahead and try a problem so you can have a concrete example to use and think about. So the hydrogen cyanide gas, HCN, this is a powerful respiratory inhibitor. This is highly toxic. Interestingly enough, it smells really nice, actually. It actually smells kind of like sweet almond smell. I used to use different hydrogen cyanides in a very small amount of that. I got in the lab one day, had to evacuate. But many people don't even realize it's out because it has a very sort of sweet almond smell that you really is very pleasant, actually. Unfortunately, it'll kill you if you can smell it in any significant amount. It is a very weak acid, and so that's 6.2 times 10 to the negative 10 when dissolved in water. A 50 milliliter sample of this 0.1 molarity HCN is titrated with 0.1 molarity NaOH. Calculate the pH of your solution. Okay, so we're going to be considering various different stages of this titrations and see what these look like, okay? And so the first thing we have is we have this 50 milliliter sample of the 0.1 molarity HCN, and we know the concentration of our NaOH, our titrant, which is 0.1 molarity of NaOH. And so we have initial amounts of the HCN we can look at. Each of these will then have different conditions. So the first thing we'll consider is 8 milliliters of this 0.1 molarity NaOH has been added. The next one we'll consider is the halfway point of this titration, so halfway to the equivalence point. And finally, we'll consider the equivalence point of this titration. Now, what I would like to point out is you may have noticed that I typically use these interactive examples to guide you through the critical thinking process that would lead to the next lesson, right? So oftentimes you're like the Henderson-Hasselbalch. We were doing the math before we ever did the Henderson-Hasselbalch equation, and we actually ended up discovering that ourselves, right? Again, that's so that you can evaluate these theories, what I'm telling you, and you understand how they work and why they work, so that you're a scientist instead of being a parrot that just, repeats whatever I say, which hopefully isn't what you're doing. All right, so A, where we have 8 milliliters of the 0.1 molarity being added. And so what this is going to be is we start off with 5 millimole, which is the 50 milliliters times 0.1 molarity of the HCN in solution. And this is going to be reacted away by 0.8 millimoles of the OH minus. Again, that is the 8 milliliters times the 0.1 molarity of NaOH. Why did I call that OH minus? That's a strong base. It's going to completely dissociate into Na plus and OH minus. And so I get 0.8 millimoles of OH minus that I'm reacting. Now, that is going to use up 0.8 millimoles of this HCN. And so once this reaction is completed, we will have 4.2 millimoles of the HCN, and we'll have produced 0.8 millimoles of the CN, which is the conjugate base. All right, now, so your major species in solution after this reaction has occurred are your HCN, your CN minus, your sodium, and your water. The sodium won't matter, we don't need to worry about that. So the position of your acid dissociation equilibrium will determine your pH. So we can go ahead and calculate our concentrations now after that reaction, after that stoichiometric. problem we just did up here. And so we had 4.2 millimoles at the end of that. Of course, the volume of that is going to be the 50 milliliters we started with, plus the 8 milliliters we added of the titrant. And so that will be 4.2 over 58. The cyanide has had some made, right? The Cn minus. And so that will be the 0.8 millimole that we made divided by the 58 milliliters again. And remember that these will give you your concentration and molarities. We assume our H plus is 0, which is going to be close enough. And so that is going to be whatever we will make in this equilibrium, right? And so that is our equilibrium reaction, which is the HCN dissociating. Our ice table will look like this, which is again just the initial plus the change gives you your equilibrium concentration. And same sort of thing as we've seen multiple times before. So if we plug these values in to our Ka expression, our equilibrium expression, then what we're going to see is, again, we get that X for the H plus, we get this equilibrium concentration here, which is what we had on our ice table, and we plug in this. Again, these X's should be pretty dang small because it's a very small number, right? And if we have a very small number for X, then this plus X and this minus X, they won't do anything. We'll just round those away. And so we can drop those. We go ahead and do the math. This divided by this. By the way, the reason that we left these as fractions is because they are both divided by 58. And so that means these will cancel. The 58s will cancel, leaving you with 0.8 divided by 4.2 times X. And so we multiply over, divide over, and we get an X equals 3.3 times 10 to the negative 9th. Notice that that is much less than 5% of these. That's a very small number. And so that will be our H plus concentration. We take the negative log of that, and that will give us a pH. Okay. And so we have seen that our pH here is 4.849. So next thing we're going to do is we're going to look for the halfway point of the titration. So you've used up half of that HCN. So again, this is our original millimoles of HCN. So thus at the halfway point, we're going to have half of that value. We're going to have used up half. So the halfway point is going to occur when we have 2.5 millimoles of HCN remaining, and we have added 2.5 millimoles of OH minus, which will have used up half. Now, another way of looking at that is going to be when you've added 25 milliliters of the NaOH, because that is 0.1 molarity, right? And again, that would just be solving this equation right here. The volume times the concentration equals the millimoles, right? So we divide over that 0.1, and we get 10 times 2.5, which is 25 milliliters. Why did I get 10 times? Well, that's what 1 divided by 0.1 is, isn't it? Okay, so at your halfway point, the HCN is going to be equal to the Cn minus, and the pH is going to be equal to your pKa. Because your base, the amount of base, is going to be equal to the amount of acid. You may remember from the Henderson-Hasselbalch equation, when the amount of base is equal to the amount of acid, the Henderson-Hasselbalch equation says your pH equals pKa, doesn't it? And so that's actually the same relationship we see here. So thus, after you have added 25 milliliters, that 0.1 molarity NaOH, and used up half of the HCN, giving you the other half of that as Cn minus, your base, right here, will equal your acid. Thus, pH equals pKa. I've given you a very, very important hint for all laboratory experiments based on pH curves. Let's look at the equivalence point, and then we can explore that hint a little. So at the equivalence point, you're going to have used up all of your HCN with OH minus. And that means you will convert all the HCN to CN minus, you'll have Na plus left, and you'll have water. You will no longer have any HCN or OH minus in solution. Therefore, the reaction that will control the pH will involve your cyanide, which is a base right here, extracting a proton from the water right here. And so that's actually your equilibrium that will control your pH at that point. Oh, by the way, this is just the Henderson-Hasselbalch equation simplified because we are plus 0. The same thing you saw before. So we've just taken the negative log of your Ka to give us our pKa, which will be equal to our pH. All right, so right here we have our cyanide reacting with water. It's going to gain a proton from the water, giving you the HCN again. And that will give you the OH minus. This is the equilibrium that will control your pH at your equivalence point. And so what we have to do first is find the initial concentration of your CN minus. Your initial concentration of your CN minus is going to be the 5 millimoles you started with over the 50 milliliters you started with plus the 50 milliliters of base it would have taken to neutralize that. How did we get this 50 milliliters of base? Well, halfway was 25, so 50 would have been the full way, right? Another way you could have gotten that is you could have used the 0.1 molarity concentration of NaOH. That it would have given you that you need 5 millimoles, right? With a 0.1 molarity concentration. And so that would be 50 milliliters to get to there. Okay, so we're going to be 5 over 100 milliliters. That will give us 5 times 10 to the negative second. Or another way of saying that is 0.05 molarity. All right, now, at this equilibrium reaction, this is again just another ice problem. So we're going to have our initial concentration. It's going to go down by some amount. That will create some amount X HCN and some amount X OH minus. Right there is our ice table, so it's a nicer way of looking at these things. And again, there's our equilibrium concentrations, just like before. So our equilibrium expression here, when we substitute these equilibrium concentrations for this expression for Kb, we solve that the same way we do for all these other problems. And what we're going to end up getting here is that X would equal 8.9 times 10 to the negative 4. And so to get the H plus, you need to take the Kw divided by the OH minus. That'll give you your H plus, which is 1.1 times 10 to the negative 11 molarity. And you take the negative log of that, and that will give you your pH, which is 10.96. So the titrations of weak acids with strong bases, some of your key points are, your equivalence point of your solution is going to be affected by the amount of the acid present in it. The pH value at the equivalence point is affected by the acid strength. The strength of a weak acid will significantly affect the shape of its pH curve. The weaker the acid, the greater the pH value at equivalence point. The stronger the acid, the lower the pH point at the equivalence point, with a strong acid being pH 7. And so right here we see some different titrations of various different weak acids. Here we see on the bottom second to the bottom, a Ka that is 10 to the negative 2. The bottom, of course, is a strong acid. And the equivalence point for this strong acid is right here at 7. The equivalence point for this next one is higher. The equivalence point here is higher, 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 and higher. And we see that the shape is quite different, isn't it? With this one almost looking like a strong acid. And as you get higher, smaller and smaller Ka values, you're going to get less and less like a strong acid looking. You'll get more of a plateau here. See that? With an initial burst at the beginning. Now, if you look carefully at these, there's two things that you have found out and been hinted at. So if you find the equivalence point for these weak acids right here, these titrations, if you go half that equivalence point, which all equivalence points, by the way, are in this rapid increase right here. They'll be part of the way through that rapid increase. So in all of these, the equivalence points are all 50 milliliters. So for all of these, if you go down to half of that, 25 milliliters, those would be halfway to the equivalence point. Another way of saying that is they would be where you have reacted half of your acid away. Another way of saying that is where the amount of acid remaining is the same as the amount of conjugate base. Or another final way of saying that, which is the one that's the important one here, is this is where the pH equals pKa, right? Half the equivalence point is where the pH will equal the pKa for all of these. And so literally if you just go half of 50, 25, you can see that this is about 2 PA, the pKa for this one is 2, see that? The pKa for this one is 4, the pKa for this one should be 6. Actually, this one's a little off, isn't it? That's funny. The graph is a little bit off. The pKa for this one should be 8. Again, that's a little off, but close enough. And the pKa for this one should be 10, which is right there. Okay. By the way, this also gives you another big hint. When you have a weak acid, this first part right here, where you have introduced a amount of base to a weak acid, these right here, before you hit the equivalence points, these are actually always buffer systems right here. So you're actually looking at buffer systems for all these. So when you look at these, you're always looking at buffer systems and then complete neutralization. That's what you're looking at. So let's do another example here. A chemist has synthesized a monoprotic weak acid and wants to determine its Ka value. To do so, the chemist dissolves 2 millimole of a solid acid and 100 milliliters of water and titrates the resulting solution with 0.05 milliliters of NaOH. After the 20 milliliters of NaOH has been added, the pH is 6. What is the Ka value for this acid? So in this case, the easiest way to do this is going to be an ice problem. So first thing you have to do is you have to do your stoichiometric problem first on all of these. So all of these titrations start with the stoichiometry. And so right here we have the 2 millimole excuse me, of HA, and we have added 20 milliliters of 0.05 molarity OH minus. That would be 1 millimole of it. So what we see here is that we have actually used up 1 millimole of those 2 millimoles of HA, leaving us with 1 millimole of HA. We use up all of our OH minus because that's the titration, right? We're using up our OH minus to convert it to the base. And finally, we're going to have made 1 millimole of our A minus. Again, that's just this amount right here, right? Okay. And so the next part will be using the equilibrium problem. Now, if you're a little bit quick on it, you would have caught on here that we actually have an equal amount of HA and A minus. And so there's an alternative that would be much easier here. But let's go ahead and go through the steps so I can give you a long, probably overwrought explanation of this. So the equilibrium problem. After your reaction, the major species that will be present will be your HA, which is your acid, your A minus, which is your conjugate base, sodium, which won't matter, and water. So the pH is going to be determined by our normal acid dissociation equilibrium. HA going to H plus and A minus. Again, this is our equilibrium expression. And so we can go ahead and do the same problem, ice problem, as we've done many, many times by now. And so we take that 1 millimole, we divide it by the volume in this solution, which is the 100 milliliters plus the 20 we added of the titrant. And that will give us this concentration initially for the HA, which is 8.33 times 10 to the negative third. Some of this will be used up, so minus x. Again, right here we have 1 millimole, and that's going to be divided by 120 again, because we have the same volume. And that again is going to give us the same number. The H plus, there's not going to be a significant amount of that solution yet, and so that will be just x. Again, we can arrange that in an ICE table. That's what I would normally arrange it in. It looks very nice and easy to figure out. So the x here is actually known because the pH at this point is 6. And so what we can do is that x is just going to be 10 to the negative pH, which is the H plus concentration. So x actually, we know that. It equals 10 to the negative 6, doesn't it? Because of the pH here. We can substitute that in to our equilibrium expression, so we just substitute that number in for all these x's. We do the math, so we add these together, then we subtract these, list them back out, and then we would do the multiplication, division, and that would give us our Ka, which is 10 to the negative 6th. By the way, if you're paying attention, you probably noticed that again, as I mentioned before, your A minus and your HA concentrations, they're the same. And so you actually, if you remember your Henderson-Hasselbalch equation, you're at the halfway point, aren't you? Which means your pH is your pKa. So you could have just taken 10 to the negative 6th, that was your Ka. Okay, so there is, of course, that easier way that I just mentioned. So you are, of course, at the halfway point. So you are at the point where your H plus concentration is your Ka. Your pH is equal to your pKa. And so your Ka is just 10 to the negative 6 at this point. All right, so the titration of weak bases with weak acids. So the steps that you have to do in this case. Now remember that you're using a weak base with a weak acid, right? And so you do not have complete dissociation for either of these, as opposed to the strong bases we looked at before. So you have to determine your major species in solution. Decide whether a reaction runs into completion. Let it run to completion and perform stoichiometric calculations if it does. Choose the dominant equilibrium and calculate the pH. So let's go ahead and try it out. We consider the titration of 100 milliliters of 0.05 molarity NH3 with 0.1 molarity HCl. So before the addition of any HCl, we had the NH3 and the water. Oh, I'm sorry. I skipped that. Okay, so when we do these problems, you're just going to set up the two equilibrium. And when you do these problems, you literally use up one species, and then you're going to set up the equilibrium for the other. It's just going to be the same problem before. Okay, so we're going to go on to the weak base strong acid titration. And we're going to consider this titration of 100 milliliters with 0.05 molarity of NH3 using that strong acid, which is 0.1 molarity HCl. So before we add any HCl, our major species are going to be our NH3 and our water. This is going to be our only available source of protons due to the fact that NH3 is actually a base here. In this case, the reaction is not going to go to completion. So the NH3 cannot really take a proton from water because the Ka value of the NH3 is fairly significant. So the equilibrium controlling the pH is going to be this equilibrium right here of NH3, the base, reacting with water to make its conjugate acid. So the Kb is going to be used to calculate our OH minus concentration. So before the equivalence point, our major species prior to any reaction are going to be NH3, the H+, the Cl-, and the H2O. The H+ and Cl-, these are due to the acid HCl. The Cl- won't have any effect in these. The H+ will work to neutralize the NH3 to produce NH4+ with this reaction right here. So the reaction will run readily to completion of that H+ given off by that HCl, reacting with our NH3. The major species present after the reaction of the NH3 with the H+ will be the remaining NH3 that you've left behind, that you weren't able to react away, the NH4+ that you've made, the Cl-, which again doesn't actually do anything in this case, and the water, which of course everything's in water. So the NH4+, of course, is what is being formed by that titration reaction of the HCl with the NH3. So this solution is going to be a solution containing NH3 and NH4+. And so these are the equilibriums of these two. This is NH4+ dissociating to NH3. This is the NH3 taking on a proton from water to give you NH4+. So essentially you can think of this is the acid, this is the base, isn't it? So we need to decide which one we want to look at and concentrate on. These are the two reactions we can look at. All right, so at the equivalence point, all of the original NH3 is going to be converted to NH4+. So at the equivalence point, you will have NH4+, Cl-, and H2O. The reactions do not attain completion for the NH4+. Your dominant equilibrium will be the dissociation of this weak acid, NH4+, which you can look at as this right here, which is your Kw, over your Kb will give you your Ka. Once we went beyond the equivalence point, well, that's just going to be straight up excess HCl. You will have used up all of your NH3. So the major species are going to be the H+, Cl- from the HCl, the NH4+ that you're making more and more of, that you've made a bunch of, right? And that was the major species at the equivalence point. And so now you're just adding more acid on top of that acid. And the water. So none of these reactions are going to occur that go to completion. Although the NH4+ will dissociate, if you have more and more H+, that's going to push the equilibrium towards the NH4+ staying together. And so as you add more and more H+, that's actually going to be what's determining your pH, that excess H+. Or another way of saying that is your H+ concentration is going to end up being your millimoles of H+ that are in excess over your milliliters of solution, because this number will just be so much greater than any dissociation of the NH4+ that occurs. All right, so this is your pH curve that we were talking about. We had a weak base that was being titrated with a strong acid. And so we start up here at basic pHs. And you add an acid slowly. You will notice again, this is a buffer system right here. We establish a buffer system, and then we break our buffer system down here. All right, so at the equivalence point, you will have used up all of your base and converted it to NH4+, its conjugate acid. After the equivalence point, this is going to just be addition of H+ from the HCl, overwhelming the system and creating this new pH, which is very low, which will be the pH of HCl eventually, essentially. Okay, now Again, I would like to note that right here, your equivalence point is at 50 milliliters again. And so if you wanted to find out your pKa for this, you can again go 1/2 of your pKa. This is a buffer system, so you can still use the Henderson-Hasselbalch equation here. So these are the different cases we talked about in that case study. This shows you the different concentrations of the NH3, NH4+, and H+ at each point, and their pHs. You will notice that in the case of the equivalence point, a weak base titrated with a strong acid will always give you an equivalence point below 7. And that's because it produces a weak acid after the equivalence point, right? That's the conjugate acid is a weak acid. Okay, so which of the following statements is true? At the stoichiometric point of the titration of a weak acid with a strong base, the pH of the resulting solution is greater than 7. There is no OH- in a strongly acidic solution. A solution with a pH of 2 is twice as acidic as a solution of pH 1. A dilute solution of acid is the same as a weak acid. Okay. Hopefully when I said this one right here, you recognize this as being something that I specifically pointed out on that graph, right? And that's a weak acid titrated with a strong base has a stoichiometric point or equivalence point that is greater than 7. The rest of these are completely just not true at all. Again, this is sort of testing your knowledge here throughout this entire chapter. An unknown weak monoprotic acid, HA, is titrated to the endpoint with 25 milliliters of 0.1 molarity NaOH, and then 13 milliliters of 0.1 molarity HCl is added. The pH of the resulting solution is 4.7. Which of the following statements is true? Okay, so hopefully you realize when you look at this that we have titrated a weak acid with a strong base here. We found the endpoint or equivalence point, right, which was 25 mils. And so half equivalent point, which would have given you your pKa, would have been like 12.5, right? Half of that. Now, when we add 13 milliliters of 0.1 molarity HCl, notice these molarities are the same. And so this actually ends up undoing a little bit more than half of this titration, doesn't it? Because we can also just react these, the NaOH versus the HCl, these will react away. So we react it with the base first, then we undo a bit more than half, 13 instead of 12.5, of that reaction, of that titration by adding HCl. And so what that means is if the pH after this is 4.7, then our pKa actually should have been a little bit greater than that because we've undone a bit more than half, right? This would actually be fairly close, and maybe it's 4.9, something like that, whatever. But it's a little bit greater than 4.7 because we're past the halfway mark. We are further left than the halfway mark. All right, so these are some of the methods that are used to determine your equivalence point. You can, of course, use a pH meter. That's actually how those pH curves for those titration curves are always measured. So this is then used to monitor the pH and plot the titration curve as we've seen multiple times before. And then graphically, you can very easily figure out things like pKa and everything else, right? Also, knowing the pH at any given point is great for figuring out the equilibrium concentrations, because then you can just plug that number in for the concentration of H+. The other way this is done, and this is a bit more common in undergraduate labs, but this can be done, this is often done in situations where you have already set up an experiment and tested it, and then you are just letting lab techs do the experiment over and over and over for a system you already understand. You just want to make sure it's getting the same results. So these acid-base indicator, this is going to mark the end of a titration by changing color. So when you reach your equivalence point, or somewhere very close to, you should have a change in color of your solution. And by the way, yes, these are all dyes. These are all acid-sensitive dyes. You can also have dyes, by the way, that are indicators that are not acid-base indicators, in case you're curious. All right, so the equivalence point will not necessarily be the same as your endpoint. And this is something that we haven't mentioned before, and you may have a misconception of. So the equivalence point is where you have used up all of your acid if you're titrating an acid, right? Or you have used up all of that weak base if you're titrating base. That's your equivalence point. The endpoint is actually just where this changes color, okay? That's what the endpoint is. So you have to be very careful in your selection of an indicator. You need to select an indicator which the error between where it changes color and your equivalence point is as small as possible. And you want this to ideally change color right at the equivalence point, or right before the equivalence point. You do not want it to be significantly different. So right here is phenolphthalein. This is the one that most of you should have used at some point. This is a very commonly used indicator. This is one of them that's in the mixtures they give you to test pools. This is colorless in the HLN form, the acidic form. The basic form is a nice pink color here. And so this is what you should do. You should be adding, in this case, we're adding base. When we reach the equivalence point here, ideally, it should change color. This is our endpoint. Now again, it changes color and that is your endpoint. If you selected this as an indicator correctly and you're using it in a proper experiment, then this would also be very, very close to your equivalence point. So this right here is the phenolphthalein. This is it in its colorless form. You'll see the H's right here. This right here is in its pink form, and you see that it has been deprotonated. So bromothiol blue, this is an indicator with a Ka value of 1 times 10 to the negative 7. This is yellow in its protonated form, and blue in its basic form. Let's assume that a few drops of this indicator is placed in a strongly acidic solution. If the solution is then titrated with NaOH, at what pH will the indicated color change first be visible? And so again, what you're looking for is you're looking for a significant amount of this to be converted from the yellow to the blue form. Now, how much are you going to be able to see? Can you see 1 out of 100 specks? No, probably not, right? You usually need something like 1 in 10. If you see a 1 in 10 is usually a pretty good indicator. You can see that pretty well. One note before we get on to this problem I want to make here. You all probably have used phenolphthalein indicator before, and this is something that I hear a lot of people ask in labs, and it really is a somewhat advanced question that analytical chemists tend to know, and not a lot of other people do. And the thing I get asked a lot is, Dr. Clausen, why does, when I put phenolphthalein into a base, sometimes the color disappears? So you have a base, you're sitting around a beaker, you put phenolphthalein in it, you expect it to be purple, right? But if you then leave it in that base, or the base is too strong, sometimes it goes clear instead, and it doesn't stay purple. And the reason for that is that phenolphthalein actually has an indicator window. So it actually turns pink between the pHs of about 8.4 up to about 10ish. And so if you're at a pH above 10, it will actually turn back clear, okay? And it only stays pink if you're between those two pHs, 8.4 and 10. Also, if you leave it under strong like UV light for too long, it can break down. And so some of the older samples will actually break down the lab over time. And so you'll have less concentration than you think. So there is some other factors going on here. Hopefully that actually solved a little dilemma you may have had in labs before. Okay, so let's go ahead and do this problem. So for our bromothional blue, our bromothional, excuse me, man, I need a drink. Blue, our Ka is 10 to the negative 7. And so what we're going to have is, this is going to have that same Ka expression we see for all acids, where the acid over the conjugate base times H plus. And so we can assume that our color change is visible when we have about 1 in 10. So you have one of these for every 10 of these. That should be a visible color change. So we assume that we can see this first hint of greenish tint. So we will be going from yellow to light blue when the solution contains 1 part of blue and 10 parts of yellow. And that would show us a green color. And so this is what it should look like. First, it's going to be yellow. When it gets somewhere in the order of like 1 in 10, it'll start looking like a very light green. And then once they're about equal, you have equal of the acid and base forms, you'll have a nice green color, right? And then eventually it will go on to a green blue. And eventually, once you have gotten rid of almost all of the acidic form, it will go on to this blue color right here. So our Ka is going to be 10 to the negative 7. That means that we should expect a color change where it is 1 in 10, which would give us this right here. So we multiply over that 10, and we'll find out that our pH, our concentration of H+, where we should be able to see some sort of color change, would first be visible at 10 to the negative 6, which would be a pH of 6. So for this indicator, we should see a greenish color at around pH 6. So if we apply this equation to the Ka expression for our general indicator, this yields this right here. And so we have the pH equals the pKa plus the log of the base over the acid. Same as all other Henderson-Hasselbalch equations. So again, this pKa is going to be that K, that's the dissociation constant for the acid form of the indicator. So again, let's try this out with a 1 to 10 ratio, which would be where we first would expect to see some sort of visibility, right? And so if we take the log of 1 divided by 10, this is going to be negative 1. And so we take the pKa minus 1, and we find out from the Henderson-Hasselbalch equation, we also get an answer that around pH 6 would be when we get that color change starting. So when a basic solution is titrated, the indicator HLN will exist virtually as Ln minus in solution, the basic form. So we would have to flip this color change. What we're looking for here is 1 in 10 of the acid versus the base, right? And so again, we go ahead and look at this. This would be the other side of the color change where we're going from blue and we're starting to get that greenish color, right? And so that would be 10 to 1. That would be the pKa plus 1. And so we should start seeing a green color when we're going down in pHs, units, at about pH 8. So our range that we expect that sort of greenish color to show up is pH 6 to pH 8. Or another way of saying that is the pK of the indicator plus or minus 1, which is 7 plus or minus 1. Right here, this is actually a nice little table. This, by the way, is actually a very useful table. So you may want to keep these slides for later on in your lives. If you go to more advanced chemistries, cough, analytical chemistry, you oftentimes have to pick your own indicators. In fact, most analytical chemistries that are good versions of the class would actually make you design a lab or two. And so this table right here will actually tell you the useful pH ranges for each indicator. And you would ideally want something that would change color for your endpoint right after your equivalence point. Okay? And so right here you would see this would be the color changes that happen at your pHs. You will notice, by the way, that some of these indicators actually have a two different color changes, like this, thymol blue. And so thymol blue actually is red under pH 2. At pH 2, it starts going orange, then it goes yellow, and it stays yellow up until about pH 8, when it'll go green, and then it'll go blue above that pH, above pH 9. And so that one's actually quite useful for indicating a whole range of colors. By the way, those little pH strips that you guys have probably used or seen before in labs, where you dot some of your acid or base on it, you look at the color and match it up to a little chart. Those actually have a small range of these indicators on them, but the major one is usually thymol blue, and that's why these are similar colors. All right, anyways, that's that chart. This is actually incredibly useful graphic. It's kind of hard to find too, so you may want to bookmark it somewhere. Now, the essentials while choosing an indicator. So the indicator endpoint and the titration equivalence point need to be as close as possible. Good indicators will produce a sharp endpoint during that titration. Now, a sharp endpoint typically is not going from like blue to green, okay? That's actually kind of hard to see. A better indicator would be things like it turns blue, okay? Or it turns pink, like phenolphthalein, right? So be aware, you want a sharp change. You don't want to go, okay, I want to stop on this indicator where it's completely green and it's no longer yellow-green. Most people are not going to be able to successfully do that. Now, complete color change occurs over 1 drop of the titrant. So a good indicator, you should have a half a drop actually is the best, but 1 drop would be the minimum there, which you put a drop in and you stir it, you mix it, and bam, the color's changed, you're done, you don't put any more in, okay? If you put in 3 or 4 drops and then the color change happens, well, 3 or 4 drops is a significant part of a milliliter. So consider the titration here of 100 milliliters of 0.1 molarity HCl with 0.1 molarity of NaOH. In your initially acidic solution, the indicator will be in the acid form. As you add OH- ions, the pH will initially increase slowly. Then, when you reach near the equivalence point, it will increase rapidly near the equivalence point. This causes this dissociation equilibrium to shift to the right because, again, you are rapidly adding OH- ions. Actually, I'm backwards here. This should be shifting this direction since we're adding OH- ions. This should be, shifting to the right because we're using up the H+, okay? And we're producing the base here. All right, so the basic ions are going to be produced. The color change can then be observed. And this color change should happen very rapidly near the equivalence point. That should be the most rapid place for that color change. So the first observable color change will be that 1 in 10 relationship, where you have 1 base molecule for every 10 of the acid molecules. And so what you find is that pK minus 1 should be where you start seeing that color shift. So this following relationship, this can actually be used to find the pKa value for an indicator that changes color at pH 7%. And so you again put in your pH value, which is 7. It's pK minus 1, so you add 1 to that, and so you want something with a pK of 8. That would be a good indicator. So thus, you would use a pKa somewhere around 8. That will change color at about pH 7. This is the ideal for marking the endpoint of a strong acid, strong base titration, which we know will reach its equivalence point at pH 7. So the indicator color change will be sharp, occurring when the addition of a single drop of titrant. There's a wide choice of suitable indicators for this. Results will agree within 1 drop of titrant when the indicators with endpoints that are as far apart as pH 5 and pH 9 are used. So right here we see a few different examples of this. We see methyl red and phenolphthalein here. And so you can see that the endpoints of phenolphthalein and methyl red occur at virtually the same amounts of added NaOH. They both occur at this very rapid climb in pH right next to that equivalence point. And so the methyl red is slightly better, but not by much. Your phenolphthalein would probably be closer to here. Your methyl red would be closer to here that you'd see it. And so, again, they are, if you could do it skillfully, I would recommend phenolphthalein, but there really is not much difference here. They would be both acceptable indicators for a strong acid with a strong base. Now, the weaker the acid being titrated, the smaller the vertical area around the equivalence point. So you may remember that graph we used with the different Kas for weak acids. That equivalence point region, where it was rapidly climbing pH, got smaller and smaller and smaller and smaller, until at the 10 to the negative 10-ish, it was almost nothing. So a chosen indicator must possess a pH range with a midpoint as close as possible to the pH at the equivalence point. So right here we see a weak acid. So here we have a weak acid. Here's our equivalence point. You see that now methyl red is not a good indicator at all. It changes color down here where you're still in a buffer region. Whereas phenolphthalein is an excellent indicator for this. If you can stop right when it starts turning pink, you will get on top of the equivalence point perfectly. So perfect, a great indicator. So in the titration of a weak acid, HA, with 0.1 molarity in NaOH, the stoichiometric point is known to occur at a pH value of approximately 10. Which of the following indicator acids will be best to use to mark the endpoint of the titration? So we have this indicator with 10 to the negative 14, 10 to the negative 11, 10 to the negative 8, or 10 to the negative 6th. Okay, so of course the pH we want to trigger is 10, right? So we want the pKa to be as close as possible to 10. And so remember, the pKa is negative log of these values, and so it's this value up here. This would be 14 for a pKa, this would be about 11, this would be about 8, this would be about 6, right? And so the closest one to 10 is, of course, 11. And that would be your closest indicator. That would be your best choice. That should be on the region near the equivalence point where the pH shoots up rapidly. All right, so let's do the titration of phosphoric acid by sodium hydroxide. Remember, phosphoric acid is a triprotic acid. And so really, when you look at polyprotic acids, they're going to look just like the monoprotic acids, as if you've done several monoprotic acids, one on top of another, okay? It's going to look like you started with a monoprotic acid, then you did another one, then you did another one. That's it. It's not anything particularly difficult, actually. It's just the same stuff you learned before. So in our first reaction, we're going to lose that first proton, right? And so at first, we're going to have our buffer region, which again, losing that first proton. And then we're going to completely neutralize it at the equivalence point. And so at your first equivalence point, you're going to end up with sodium, which again doesn't matter, from the NaOH. You'll end up with the H2PO4, which is your conjugate base, and will be your acid for the next region. And you'll end up with water, of course. So once you've added more sodium hydroxide to this, well, this is an acid, isn't it? So the next portion after you hit this equivalence point is going to be the titration of H2PO4 using sodium hydroxide. And so it's going to be this reaction then, which is H2PO4 being neutralized to HPO4. And once you reach this equivalence point, again, you're going to use up all of this when you reach the equivalence point. And so you will be HPO4 for your major species, and you'll still have the sodium and water. Sodium again doesn't matter. water is water. It's what everything's happening through in these. Okay, so the addition of sodium hydroxide beyond the second equivalent point, well, again, your product at that second equivalence point was HPO4. This was another acid, wasn't it? So when you add more sodium hydroxide after that, you are just doing another titration, this one of HPO4. So you start titrating HPO4 using OH minus, and you get the PO4 3 minus, which is its conjugate base. And this one is no longer an acid anymore. This is just completely a base. You don't have to go any further. You're done. Whenever you reach this equivalence point, from then on, you're just adding an AOH. That's it. Just like every other time you looked at these. All right, so this shows you a summary of those major species presence and different points and titrations that we talked about before. This one being for a polyprotic weak acid. Right here, this is the titration curve of a polyprotic weak acid. Again, this is going to be your first deprotonation. This right here, it's a buffer right there. This right here is your equivalence point. Once you've reached the first equivalence point, you're just going to start titrating that major species for your next region, which again, this will be a buffer region again, and this will again be your equivalence point, which will be where you've used up all of the H2A to give you the single proton one. And finally, you have used up the last proton. That's going to give you just the basic form of this species, and from then on, it's just adding OH minus to increase the pH to the maximum that sodium hydroxide is going to be able to give you. All right, now, you will notice that these look just like monoprotic acid titration curves, just that you've taken 3 of them and stacked them on top of each other. See that? That's it. So when you do these titrations, you can really look at it as if you're doing 3 monoprotic titrations, using the Ka1 here, the Ka2 here, and then the Ka3 right here. And you can just do this using the Henderson-Hasselbalch equation with Ka1 here, Ka2 here, Ka3 here. So your pH can be determined at the first 2 equivalence points by using the average of the corresponding pKa values. The pH values at the half equivalence points can be estimated as equal to the corresponding pK values. So the pH at the first half equivalence point is going to be approximately equal to the pKa1. The pH at the second half equivalence point, so this is the first half equivalence point about here. This one will be the second one about here. This one will be the third one right here. That's what these are indicating. Now, that means the pH at the third half equivalence point would be approximately equal to the pKa at 3, which would be your third deprotonation. Your pH curves can be used to determine the number of acidic protons on a particular acid. If you have one equivalence point, one of those rapid gains, then you are going to have a monoprotic acid. If you see 2 equivalence points, so you have 1, 2 rapid gains, you have a diprotic acid. And if you have 3 equivalence points, of course, you have a triprotic acid. The pH values at various points on the curve, these can be determined by using the appropriate pKa values in a Henderson-Hasselbalch equation. So, again, the half equivalence points are always going to be the pH equals pK. All right, so one of the things that you may not have realized here is your pH here can be determined by the first 2 equivalence points by using the average of the corresponding pKa values. Okay, so if you take these average corresponding pKa values that you get from here, that will actually give you a very, very good approximation of your equivalence point here. And this is something that you don't truly get to recognize and realize is very useful and strong component until you get into very complex problems that you might see in like analytical chemistry. But you were actually taught it up here in general chemistry too. So that is something you can do. If you have the pKa values for two sides, you can actually figure out an approximate a pH value for your equivalence points. And that means that you can then know approximately where you should see endpoints happen, right? And so you can actually help your titration if you're doing a titration by doing just a little back of the note calculation. It's a little trick you can use if you're working titrations. Okay, folks, you have a great day and take care now.